first, short summary about myself, if it's working. Yeah, I was born in Germany, and right now I'm living in Leipzig. I also studied in Leipzig. I studied chemistry, where I met my good friend Isaac. And more than 2 years, I'm working at Malvern Panalytical. So first at all, where is Leipzig? So if you have a map of Europe, you can see that Germany is in the middle or in the center. And there's here the capital of Germany, it's Berlin. And if you're going 100 to 200 kilometers down, where you can find Leipzig. Leipzig is a really young city, and we have a nice university, also a lot of historical place. And yeah, if you want, you should visit Leipzig one time. Yeah, what is my company doing, Malvern Panalytical? We are manufacturing of scientific instruments, and our company statement is, we are big on small. So why we are big on small? Imagine you have objects in the meter or centimeter range. It's not a problem. You can use a ruler to determine the size. But if it's becoming smaller and smaller, for example, a human hair, it's in the micrometer range, or blood cells or bacteria, about 1 micrometer, or especially for really, really small things like a virus, this is in 100 nanometer range, or DNA, it's in 1 nanometer range, you need other techniques. And we have these techniques like the static light scattering, which can measure particles from millimeters up to nanometers. Also the dynamic light scattering, which are going down to 0.3 nanometer. And also it's interesting to term the elemental analysis, and we can do this with X-ray. So there is this X-ray diffraction for structure and X-ray fluorescence for the elemental analysis. And X-ray is a really high energy radiation where you can penetrate all kinds of materials. So before the Malvern Panalytical, there was 2 companies called Malvern and Panalytical. So Malvern is a British company founded in the 70s, and it's well known due to the particle size characterization, especially in the nanometer range. And if you're a really good company in England, you got this Queen's Award from the Queen of England, and Malvern got it 5 times. So the company is very innovative and helps people to compete against cancer or other disease. And on the other hand, there is this company Panalytical. It is a former Philips company, and this company is all about X-rays, so this high radiation. And Panalytical is the pioneer for the first X-ray diffractometer, and from this you can determine the structure and also your elemental structure. Yeah, and right now we are merged together to Malvern Panalytical. Yeah, so let's go back to the topic, how batteries will change our life. So we have this big problem with the climate change. Here we can see a picture of a coal power plant, and you see this coal power plant pollutes a lot of the air, and we have this greenhouse effect that the temperature is increasing and increasing more. You can see here in the graphic the last 100 years, and we have this temperature increase. And for this, we need new technology. We cannot use our old coal power plants. We need renewable energy, and we already have this. So for us, in one case, we have this wind energy and also the solar energy, but there's a problem, we cannot store the energy. And for this, we need these batteries. And the old technique is with lead batteries, where you can store the energy and also transport the energy to another place. For your mobile phones, there are the lithium-ion batteries, and maybe you are familiar with this. There's new car company, Tesla, they're using this Panasonic lithium-ion batteries. And also more and more companies or car companies will use this pouch cells. There's also another technique with all solid-state batteries. So how does a battery work? There's this problem with lead-acid batteries. So most of the cars have lead-acid batteries, but only for starting and for light. So you cannot replace the motor. And this is due to the low energy density. So if you have a Tesla, which have a starting weight about 1,400 kilogram, and you want to use lead batteries for a motor, there's a big problem. You see here you have a miles per charge for 70 miles. And for this, you have to use 2,500 kilogram of this lead batteries. So it's really heavy. And another case is the volume. So you have only 15 cubic meters in your car, and you will lose 5 of them due to the lead acid batteries. And also the lifetime is really low, only 100,000. And so for the new cars, it's much better to use lithium ion batteries, where are lighter, have a higher density, also higher energy, so you can have more miles. And also there are not so many problems about charging and discharging. So right now, how does a battery work? So you have two main parts. You have here the cathode, and on the other side, the anode. And when the battery is stored with a lot of energy, you have here your graphite structure. This is the graphite, these rings. And between these rings or layers, you have your lithium. Lithium has 3 electrons, and from this, or can give a spent 1 electron. And when this electron is traveling through this wire, you can use here the power, and then the electron is going to the cathode. And then this happens all the time, that the lithium gives the electrons away, and the electrons are stored in the cathode. And then there's a problem of the charge. You have a lot of electrons at the cathode, and there's a charging problem, so you need counter ions. And for this case, you're using your lithium ion. So when the lithium is gave 1 electron away, you generate a lithium ion, positive charged, and this lithium ion can travel to the cathode. And for this, there is a separator to avoid the contact between the cathode and the anode, and only the lithium can pass through the separator. And furthermore, there's an electrolyte necessary, which is a liquid or medium where the lithium ions can travel. And if you want to charge your battery again, you will put the voltage here, or the charger, and then all the electrons are traveling back to the anode, and the anode is charged. So this is the principle of a lithium-ion batteries. So how looks the lithium-ion battery inside? So for this, you can take your mobile phone and destroy it, and to get out this lithium-ion battery, but you don't have to do it. We did it already. And for this, you have a hard case to protect the batteries. And here you can see our battery cell. And the battery cell is packed or folded, and we unfolded the battery cell. And then you can see here, this is our anode. You have a copper foil, and then you have your graphite material. And also here's a separator. We see it before. And on the other side, there's the cathode. It's an aluminum foil with the cathode material on this. Here you can see it again. Here's our cathode with the aluminum foil. Here's our anode with the copper foil. And the foil is necessary to collect the electrons. The material is not good in collecting electrons, but the foils are really good. And here you can see the separator foil again. Yeah, how we can manufacture lithium-ion batteries. Here's the process. So we already know it, that we have an anode and a cathode. For the anode, we use this copper foil. We take graphite, carbon, and dissolve it. And from this graphite powder, we got a slurry. And then the slurry is coated on our copper foil. And on the other hand, the same with the cathode. You take your cathode powder, normally is nickel, manganese, and cobalt, mix it with carbon and also a binder to generate the slurry, and coat it or coat your aluminum foil. And then you have to combine your coated copper foil with your coated aluminum foil and a separator and stack it together like this way. And when it's done, we also need our electrolyte. Where do we have to use the electrolyte? The electrolyte is the medium where the lithium ion can travel. And after this, we got this nice battery cells. And Volkswagen, a big German car supplier, we are also good in manufacturing lithium ion batteries. And I will show you a short video about this. So here you can see it in a small scale. We have here the mixing unit. And I think, yeah, we will have a look inside. Here you can see the slurry. This is mixed together, the anode or the cathode material. And after mixing, it's coated on our copper foil. Here you can see the coating process, where we have to generate a really homogeneous thickness. And after this is dried with the oven and packed together. So this is called calandering, that you are pressing the battery materials together to have a higher energy density. And after this coating process, the cell is cut in the right size. So here's the cutting process, and then you have your battery cells. Yeah, and two main parameters are really important. It's the particle size and the structure of your material. So for the particle size, it's good to have really small particles. So if you have really small particles, you have a higher energy density and more power. And when you can, if you use it for a car, you can have higher ranges, that your car can travel about 1,000 kilometers. But we have a problem with the charging. So the electrolyte is degrading your particles. And if you want to charge your material or your battery, it's degrading it. And after a while, you lose your complete active material. So in this case, if you want to charge really fast, you need bigger particles. But there's another problem. When your particle is too big, you have an inactive material core inside. So it's really important to control your particle size. If you want to have a material where you can charge it really fast in minutes, you need bigger particles, or for higher power, smaller particles. And the particle size, it's in the micrometer to nanometer range. And for this, you need a technique to determine the particle size. And we can do it with laser diffraction. So how does laser diffraction is working? For this, we have a particle, and when the incident light, especially its monochromatic laser light, hits the particle, and then the light is scattered. And it depends on the particle size. So if you have a big particle, the angle is small. And if you have a smaller particle, the angle becomes bigger. And you can see it here from an experiment. You have here your material. In this case, it was 5 micrometer. Go put it on a, or the laser is attacking this material. And then you're seeing this scatter pattern that you have for big particles, small angles, and for smaller particles, larger angles. And from this pattern, you can calculate the particle size. And you can do it with this instrument from us with a master size of 3000. And here you can see this particle size distribution. And it's really easy. You put only your material here in the tank, and then the instrument is measuring. And you can determine particle sizes from nanometer up to 3500 micrometer. And here we can see 2 cathode materials. It's this lithium iron phosphate. This one, this is a little bit more than 10 micrometers. And also we have this lithium cobalt oxide, which is a little bit smaller. And if you don't want to put all the time the sample into the instrument, there's another instrument which are doing this all the time automatically. It's for online or inline analysis. So here you have your mill or your mixing unit, and every 10 seconds the instrument is taking a sample, and then it's measure the particle size. So you don't have to take the sample, and this is really nice for process control. If you have a big plant, you can check all the time your parameters, are the particle size correct, and you don't have to do anything in this case. Yeah, this was the first important parameter, particle size. And another one is the structure of the particles and how you can determine the structure of your particles. You can use for this X-ray diffraction. So X-ray diffraction is a technique to investigate your crystal phase. And for this, you have this X-ray tube or X-ray source. And when the X-ray penetrates your sample with really high energy, and from this, you got signals, something like a reflex, and the detector is scanning the angle area. So it starts here at 0°, and when it's moving this way and checking all this 2 theta area, and when you got this spectra, so in XRD it's called a spectra, it's a diffractogram, and when you have your reflexes here, and you can determine your crystal phase, or you can compare it with a database. And this is the case how we deal with battery materials. We measure the material, got some reflexes, and when checking it with a database, you can see the red one is from the database, the blue one are the original data, and then you can say, I have the correct material, or you can also quantify it. I have 90% of this and 1% of impurities. And yeah, there are different cathode materials which you can detect. There is this lithium cobalt oxide, which is really common, also called NCM or NMC. Then we have the lithium manganese and also the lithium iron phosphate. And there are 2 battery types that are really often used. It's the NMC 611. So what is the code NMC 611? N is for the nickel, M for manganese, and C for cobalt. And 611 is the parts. So you have 6 parts of nickel, 1 part of manganese, and 1 part of cobalt. And the trend is to increase the nickel content due to the toxicity of cobalt. So the next batteries have this 811. And you can see all the time we need this lithium for the counter ion. So there's also a high demand on lithium. And the question is, do we have any problems with the lithium? And when we can check the resources of lithium, so there are 2 big areas of lithium. It's Chile and Australia. And the resources are about 8,000 in Chile. And right now the production is really low. It's about 16. So you can see we have a lot of lithium, and I think there's not a big problem from my side, but there's not enough lithium available. And how you can gain the lithium? There are 2 ways. One way, which happened in Argentina or Chile, it's from this brines, lithium-rich brines. You have to imagine something like a lake. And then the sun is drying this lake, and you can generate your lithium salt. Or on the other hand, there is this lithium mine in Australia where you got your lithium ores. Here you have a lithium ore, and then you got it from this mine. And then you have to crush the material, doing some extraction process. It's called flotation. And after this, you make a thermal treatment. And for this, it's really important to determine the right structure. And so you can use again this XRD method, X-ray diffraction, where you got the mineralogical composition, and you can see how much of the special lithium minerals you have in your materials, and can make prediction about the quality of your lithium. Yeah, this is about the lithium. What's with the cobalt? Cobalt has a really nice color if you have a mineral. Here you have the blue color of the cobalt, but there's a problem. Cobalt is toxic, and there is a problem on the demand of cobalt. So there was a lot of price fluctuation in the last years. You can see it here. There was in 2018 a really high price of cobalt, 3 times higher than right now. And this is about the production. It's a side product from the nickel and copper production. And there's only a small area where you can get this cobalt. And this is in Africa. It's in the Congo. So all people try to replace it because there are some political issues and problems there. So the most of cobalt, is coming here from Congo. There are still other areas where you can get the cobalt, so from Russia and also from Australia. But all the people try to avoid the cobalt due to the toxicity and the limited access. And another important material is the nickel. And you can nickel from Canada, and the biggest amount are here in the Pacific Islands, and also from Russia and from Europe, especially in Finland. And how you can get the nickel? You do an extraction of nickel sulfide, iron sulfide, and copper sulfide. And then you got your nickel from it. but it's a really complicated manufacturing process. And for the battery cells, you need a really high purity. So at the end, you have to do a purification of the nickel. Then you can use this Mohn process. And so I'm a chemist. I have to show at least one chemical equation. So here we have our impure nickel. And when you will put a gas on it, it's carbon monoxide. And from this, at higher temperature, you will get a complex, this nickel cobalt, this nickel complex. And when you heat it up, it's destroyed again. And then you got your nickel in a really high purity, but you can use it again for the battery cells or other approaches. And for this, you have to check all the time the elemental analysis, and we can do it again with our X-ray techniques. Here you can see we have this X-ray, the ores, the nickel ores, and we are checking the elemental analysis with one of its instruments. And we helped two big companies. It's this Russian company, Nornickel, and a German company, BASF. And there's a big nickel mine in Finland, in Harjavalta, and you can see they built a really big plant to generate there the nickel. And the idea is to produce better electrodes. So with a higher nickel content, the battery have much more power. And for cars, you generate a higher range. So if you want to replace the normal combustion motor with an electrical motor, you will generate ranges from 800 to 1,000 kilometers and also decrease the charging time. This is also right now a really big bottleneck. And with this new technology, it shouldn't be a problem again. Yeah, what are the trends? The trends is there's a really high demand on battery cells. And on the other side, you have to produce it in a really low cost. And for this, you need gigafactories. It's not small factories. We have to use gigafactories. And maybe you heard about Tesla. We are planning a lot of these gigafactories and also other companies. And I will give you a short overview about what's going on in Europe. And in Europe, a lot of companies announced or want to build this big gigafactories for battery cells. So there is this Norwegian company, Freya, and also the Swedish company who will build big plants for the greenest batteries. Also some known companies like LG and Samsung, also Tesla. The French government is building battery cells with Peugeot, with PSA Group, and also the Germans with Volkswagen are manufacturing in Germany with battery cells. And there's also an announcement of the biggest Chinese battery cell company. It's CATL, and they will build the biggest gigafactory ever with 100 gigawatt hours. Yeah. What are the other trends or what's going on in the research? You see we have some problems with the lithium, the cobalt, and also with the nickel. And there's a professor in Germany who developed new batteries, and these batteries are from organic materials. So, for example, we can use waste to build this new organic materials, and then we can build up with battery cells. And here you can see this new battery cell. And I want to show you a second video. And it's still possible to generate electricity from some organic materials. So there is this lemon experiment that you can use the lemon for a battery. The voltage of a lemon is not really high. It's about 0.85 volts. And if you want to use a 3 volt LED, of course, you have to use four lemon batteries. And it's a really simple experiment. You need some zinc nails and also some copper. And then you will combine all the batteries or the lemon batteries together. We can see the zinc nail and also the copper material is insert. Then you will contact it with a wire. And after this, we can connect it to our LED, and it starts with lighting. So the problem with the lemon is you cannot recharge it. but this professor found materials where you can charge it and recharge it from organic materials. So let's go back to the presentation. This was the lemon experiment. And what are the future trends? I think the future is that most of the cars will be replaced by electrical cars, like here, the new Volkswagen ID.3, and also the scooters. So I like it to be in Italy, but I hate the scooters all the time. So I cannot sleep because they make so much noise. And I hope if they replace it by this combustion engine, and if you have electric scooters, they are not so loud, and the world become more, not so many noise. And also we have more clean air due to the energy we can use from renewable energy, renewable plants. And another point is with wearables. Maybe you heard about this, or maybe you already use this wearables, that you can use smartwatches or also smart glasses for navigation or to see Netflix. And all these wearables, like smart shoes or smart belts or smart bracelet, they need energy. And this energy comes from the battery cells. And these battery cells have to be really small. And there's this one German company, Varta, who produce really small batteries. And these batteries have, of course, a high energy and also a long lifetime. And these are the future trends that we have to use with batteries to use all the wearables. And all in all, you see batteries will change our life. We have a big impact in cars, in e-scooters, in the wearables, and hopefully we will generate clean air and a better future. So this is the end of my talk. Thank you for your attention, and if you have any question, feel free to ask me.
Perfect. No, thank you very much, Max. I'm really I really like the presentation. I mean, especially because it's not my topic, it's not my expertise area. So I would like to ask someone if they would like to ask a question to Max about the topic and the conversation. If someone wants to ask, please feel free to only open your microphone and ask. Because if not, I will start with the first one. Max, I have a question. I mean, when you are talking about this NCM and you are moving to this 811 because you want to decrease the percentage of manganese, is right?
Of nickel, sorry.
Of nickel. Is it possible to increase that ratio much more? I mean, you told me about, you told us about 811. Is it possible to go further, like 1011 or much more?
All the companies try this, but there's a problem. There's a safety problem. If you increase the nickel content, the battery become more and more reactive. And it's a safety issue. If you overload the battery, it starts with burning. So I think you're right. In the future, we will increase it to more, to 1011, 10011, and you will have more power. But there is this safety problem that we will start with much.
Max, and what about the difference, for example, in those cathodes materials, you have cobalt, manganese, and iron. Is there a main difference between using iron and manganese on the cathode?
It depends. I think the first one are the much more energy density, the higher quality, but the lithium phosphate batteries, they are really good for recharging and charging, and they are also cheap due to the iron. And a lot of Chinese manufacturers are using these batteries right now with LFP cells, lithium iron phosphate cells, and they are placed in the cars. So we have Chinese cities where have a lot of problems with public transport, and for the big buses and cars, they are using this LFP batteries.
Okay, so that means those ones are cheaper.
Yeah, this is cheaper.
Okay. Yeah. And my last question is about the last topic that you were telling us about, for example, this lemon experiment. Do you see in the future developing this kind of batteries, this organic material batteries? what's your opinion? Because looks really
Yeah,
nice and it's cool to see how we can start using organic materials, but is it available? Is it reachable? We can reach a moment that we can find that?
Yeah, I asked the same question on a conference. So the materials are organic. It's really easy to access to the material. Also, the energy is really high, the voltage. But there's one problem, it's the volume. So the density is really low. So if you want to use it for your mobile phone, you have to buy a whole container. So the volume is too big, where the density is right now too low. And yeah, you need really big space for these organic batteries. But I think in the future, we will improve this and increase this. And maybe you can look for a hybrid solution, insert some heavy metals like nickel or cobalt in this to increase the density.
Okay.
Yeah, but at the end, we will.
Sorry, sorry.
No. I was finished.
If someone wants to ask a question, please feel completely free. Stephanie, please, you raise your hand.
Hi. Well, my question is also like a little bit about your opinion. Do you think in the future we will only use electric cars, or do you think that that's more kind of a dream?
Really good question. So I hope most of the cars becoming electric, because there are a lot of advantages. For the motor, you need less parts. The maintenance is much easier. Also, you don't need the petrol. You can use this battery energy or from the renewables. But I'm not sure. It's maybe also a governmental thing, which will be supported or protected, and yeah.
Okay,
we will see it. Yeah.
I think we have also Victoria. You raise your hand. Please feel completely free.
Okay, so when I was paying attention to the presentation, I saw like these stocks and where the lithium came from, and I started to wonder, like we are using lithium, and that's great. It works pretty marvelous, but the thing is, it's not an infinite resource, and I highly doubt it will disappear, to see it in some way, anytime soon. But is there any other kind of element that works as well as lithium, or one that is being tested, or for now all we have is lithium, and if something happens to lithium, everything's done?
Yeah, also good question. So there are also other materials like lithium, but in one case, I think we have a lot of lithium right now. And another point is we can recycle the lithium-ion batteries. So there are many ways to doing this recycling and to get back the lithium, also the cobalt and the nickel. And there are some other materials, I think it's sodium batteries, but with sodium batteries, they are more for stationary things. Like if you have a hospital and need some second power plant, you can save this in this sodium batteries. But I think lithium is one of the most interesting elements, and this is best one for charging and recharging.
Max, and now we have a question of Pamela Campos.
Hello.
Hello.
Well, I was in Switzerland in 2018 in an exchange year. Well, and there I saw like how the buses works with the battery, and I always hear, but I'm not sure if that's how it works. But well, they have a battery, and so when the people that I see in the bus, when the bus stops and the people go out of the bus, they said that this battery is in a rechargeable. Like, my question is how this battery works, when they have to like have more energy, or how is it works, like yeah, like when the battery will, okay, I don't know how to say that. Like, okay, ich sage das auf Deutsch. Es ist
Okay.
nicht
You're speaking German, nice.
ja, ja. Also, die Sache ist, dass wenn ich drinnen in dem Bus war, zum Beispiel, dann, ja, dann der Bus in die Haltestelle, zum Beispiel, die Leute draußen gehen. Ich habe es gelesen, dass in diesem Moment der Bus nimmt Energie von, ich weiß nicht, wenn das ist von einer, ja, vielleicht von, das ist meine Frage, von wo nimmst du die Energie in diesem Moment? Weil Sie sagen, dass in 15 Minuten, wenn die Bus ist nicht in Bewegung, sie nimmt die Energie von irgendwo, aber ich weiß nicht, von wo ist. Also das ist meine Frage.
Okay, so I try to, repeat your question on English. So your question is how the bus is charged when it's not moving. Is this the question? So if you're at the
Yes.
stop,
Yes,
okay.
that's my question.
I have no idea. So I heard about that if you are traveling and you start with braking, then you can recover your braking energy to this electrical energy and it's stored in the battery. But I think if the bus stops, I have no idea how you can charge your battery. Maybe there is something like a plug with magnetic that you can charge it, or it's using solar panels and so on, but I'm not sure.
Okay, really good. Dankeschön, Pamela. Max, you were talking about that there is possible to recycle the lithium, right?
Yes.
How normally? I don't know if you know the answer. If you have a quantity of lithium, how much can you recycle? You can recycle everything, 100%. I don't know.
It depends. So this is still research.
Okay.
So the batteries are not in so big volume, and for the car batteries, it's more interesting. And right now it's starting, but there are 2 companies right now in Germany and also a lot of research, but I think it's 98 or something, I read it. And there are 2 ways. One way is crush it and heat it up. And the other one is a cold way, crush it and put it in special solvents and then separate all the materials.
Okay.
Yeah.
So, and that means that, for example, right now, many of the batteries that we have on the market are from renewable lithium?
No, I think it's all the time new lithium.
Okay.
Because we have higher quality.
Okay.
So if you're using this renewable thing, you have some impurities, and this makes some problems right now. Yeah.
That's
all the time we are looking on the best quality and on the cheapest way to get it. And I think this is still the lakes and the ores.
No, but I'm asking this because I don't remember who was the Victoria, I think, was to ask you, but I think it's a really interesting question because we know that lithium is going to finish in a moment in the world. There will be a moment that there will be not any more deposits. And I think Victoria will want to ask something again. Victoria, please.
My apologies for that. Point is, I'm following with this reasoning that we can recycle lithium. Well, we can recycle lithium if it comes to a place where it can be recycled. But currently, and I have seen it and I have done it because I had no idea this could be recycled and I had never heard about it until now. Like, we get the batteries, they run out, and we throw them out in the trash. And when we throw them out in the trash, they are crushed. But inside, they have toxic elements. And I was kind of wondering how that affects like the ecosystem and how damaging that is. That as a norm, a lot of people throw away the batteries and they just get crushed and they get mixed with organic things and a lot of different materials that can be found in the trash, and then they end up being dumped in some place where they gain access to the earth and water and all that. So how bad are we damaging, or is that not damaging at all?
Yeah, good point. Yeah, we have some problems with the cobalt, and also the electrolyte is really toxic right now for the lithium-ion batteries. And yeah, you're right. I think especially for mobile phones, we will put it in the waste. But the biggest part will be electrical batteries. And I think for this, there are governmental issues and so on. And we will, for this car company, car sales, it will be more regulation and possibilities for recyclable material. Yeah. And hopefully we can also change the chemistry, go back from the lithium-ion batteries and go to the organic, which will be more, better for the environment.
I think that question is really important because many people, at least in Costa Rica, Max, is to start thinking about this environmental situation. How can we decrease the problem with the environment?
Okay. So how is the situation with batteries and battery cars in Costa Rica and the energy?
That's a really good question. I don't know if someone here is attending that has experience on this, but I don't know. But I think it's a really interesting topic, Max. And I hope some of the students will like to do the thesis on that topic because I think it's really, really important.
Yeah, I think it's a hot topic and it's also really focused for a better world, and all the companies are doing this and all the research institutes. We are not. Yeah.
Sorry.
No, I'm done. Yeah.
No, especially Max, when you think that many of the accessories and the stuff that we are using currently, we need the batteries. So it's something that we need to still working on the research on that topic because it's something that we really need.
Yeah.
I don't know if someone else want to ask something or do a final comment about the presentation. I think has been a really nice conversation. I appreciate that the people was asking questions. If not, I want to thank Max.
Also again, thank you.
I hope that it's already late in Germany, and for us, it's really important that you took a time to be with us. And I want to thank everybody who joined us today. And I want to remember you that you will have the information of the following Café Virtuales in our social media, Instagram, Facebook, our website, acstech.com, and also on the YouTube channel. All this information you can also follow it on the American Chemical Society website. Thank you very much. Muchas gracias a todos por su asistencia, por haber estado por acá, y les agradecemos que nos continúen apoyando posteriormente en los siguientes cafés virtuales. Max, ich hoffe, du hast eine gute Nacht.
Ja, vielen Dank. Adiós.
Hasta luego, Max. Muchas gracias. Chao.
Yeah. Gracias. Ciao, ciao.
And thank you very much, everybody.